In the previous lecture, we've learned the chain rule for multivariable functions, and we've also learned the tree diagram method to help us to write down an equation for the chain rule without having to memorize the formula. In this lecture, let's look at 3 examples of finding the derivatives of multivariable functions using the chain rule. Here's the first example. If z is function of x and y, where x is sine of 2t and y is cosine of t, find the derivative of z with respect to t at t equals to 0. Let's draw the tree diagram first. So we have the function z, that is a function of x and y, and both the x and y are function of t. And note that at the end of the tree, we only have one variable, the variable t. So we can also express the function z as a single variable function, the variable t. So its derivative, we will use the normal derivative and not the partial derivative. So the total derivative of z with respect to t, using this tree diagram, it is also the partial with respect to x, then times dx over dt. And I use the total derivative for x with respect to t because x is a single variable function. It is function of t only. Then plus, along the right side branch, I have dz over dy, and then times dy over dt. Now let's find the derivative of each of them. So the first one, we have the partial derivative of z with respect to x. That is, we want to take the derivative of this with respect to x. By treating y as a constant, we get 2x times y, then plus 3 times y to the power of 4. Then times derivative of x with respect to t. That is, we want to take the derivative of this function with respect to t. And we get 2 times cosine of 2t. Then plus the partial derivative of z with respect to y. So we'll take the derivative of this function with respect to y. And we get x squared, then plus 12 times x times y cubed, then times derivative of y with respect to t. That is, we want to take the derivative of this function. Derivative of cosine of t is negative sine of t. And that is the derivative function. So if we want to find the derivative at t equals to 0, then we substitute t equals to 0 into this function. But note that in this function, we also have the x and the y. So I also need to find at t equals to 0, what is the value of x and what is the value of y. So I substitute t equals to 0 into the function. I get x is sine of 0, that is 0. And y will be cosine of 0, so that is 1. So I substitute t equals to 0, x equals to 0, and y equals to 1 into the derivative function above. So the derivative of c with respect to t at t equals to 0 is 0 plus 3, then times 2 times 1 plus 0 plus 0, then times negative of 0, which equals to 6. So that is the derivative that we want to find. And here's the second example. If z is function of x and y, and the rule is e to the power of x times sine of y, where x and y are both function of s and t. Let's write out the expression for the partial derivative of z with respect to s and with respect to t. Let's draw the tree diagram for this function. So the function is c, which is a function of x and y. And x and y are both function of s and t. So below x and y, we will have 2 more branches, function of s and t. Similarly for the y. So for the partial derivative of z with respect to s, we can see that at the end of the tree, we have 2s. Then we follow along the branches. So dz over ds. Along the left side branch, we have dz over dx, and then dx over ds. And here I use the partial derivative for x, since x is a multivariable function. It is function of s and t. Then along the right side branch, to get to the s, I need to pass through y, so dz over dy, and then y to s, so times dy over ds. Then let's find the derivative for each of them. For the first one, dz over dx, so I treat the y as constant, and I get e to the power of x times the constant, sine of y. Then times dx over ds, so I treat the t as constant, and I get t squared. Then plus dz over dy, so I treat the x as constant, and I get e to the power of x times cosine of y. Then times dy over ds, so I treat the t as constant, and I get 2 times s times t, the constant. Then I can also substitute the x and y back to this equation. So this equals, I'll bring the t squared to the front, then times e to the power of x, and x is s times t squared. Then times sine of y, and y equals to s squared times t. Then plus, I bring the 2st to the front, then I have e to the power of x, where x is s times t squared, then times cosine of y, where y equals to s squared times t. How about the other partial derivative? So we want the partial derivative of c with respect to t. So if we look at our diagram again, at the end of the tree, I also have 2t. One is along the x branch, and the other is along the y branch. So using the same method, I would get dz over dt equals to dz over dx times dx over dt, then plus dz over dy, and times dy over dt. Note that the dz over dx and dz over dy will be the same as the first partial derivative. The only thing that's different is only the dx over dt and the dy over dt. So this also equals dz over dx is the same, so e to the power of x times sine of y, then times dx over dt, where x is s times t squared. So this derivative will be 2 times s times t. Then plus dz over dy, which is the same as the previous partial derivative. That's e to the power of x times cosine of y. Then times dy over dt, that will be s squared. And I can also substitute the x and y back to this equation. So I get 2 times s times t, then times e to the power of s times t squared, and times sine of y, and y is s squared times t. Then plus s squared, then times e to the power of x, and x is s times t squared, then times cosine of s squared times t. And here's the last example. If u is function of x, y, and z, where x, y, and z are all functions of r, s, and t. And we want to find the value of the partial derivative of u with respect to s when r equals to 2, s equals to 1, and t equals to 0. This function sounds more complicated. It is a function of 3 variables. And for each of the variable x, y, and z, they are all functions of other 3 variables, r, s, and t. But the principle is the same. We draw the tree diagram, then to find how we can go from z to s, which is the variable that we want to differentiate with. So this tree diagram will look like this. We have the function u, which is a function of x, y, and z. And for each of the variable, it is also a function of three variables, r, s, and t. So that would be the same for all three variables, r, s, and t. Same thing for the z, r, s, and t. The partial derivative we want is the partial derivative of u with respect to s. Then I check at the end of the tree, I see that I have 3s. And to go from u to this 3s, the first branch, I need to go through the x and then to this s. And to the second s, I need to pass through the y, then to s. And the third branch, I need to go through z and then to s. So if we expand this partial derivative, the partial derivative of u with respect to s, then we get du over dx times dx over ds, then plus, through the middle branch, du over dy, then times dy over ds. And finally, through the right branch, du over dz times dz over ds. Then we find each of the partial derivatives. For du over dx, we treat the y and z as constant, and I get 4 times x cubed times y, and the second term would just be 0. Then times dx over ds, so I treat the r and t as constant, and I get r times e to the power of t. Then the second term, du over dy, I treat x and z as constant, and I get x to the power of 4 plus 2 times y times z cubed. Then times dy over ds, which equals to 2 times r, then times s, and e to the power of negative t. And the last term, du over dz, so I treat x and y as constant, and I get 3 times y squared times z squared. And finally, dz over ds, so I treat r and t as constant in the function z, and I get r squared times sine of t. And that is the partial derivative function with respect to s. Now we want to evaluate the value of this partial derivative function when r equals to 2, s equals to 1, and t equals to 0. We can first substitute these three values into the x, y, and z functions. We have 2 times 1, then times e to the power of 0. So we have x equals to 2 at this point. Then for y, we have 2 times y squared times e to the power of negative 0. So y is also 2 at this point. And last function, z, we have 2 squared times 1 times sine of 0. Sine of 0 is 0, so z at this point is 0. So the last step is to substitute these values into the partial derivative function that we just found. So this equals 4 times 2 cubed and times 2, that is 64. Then times 2 times e to the power of 0, that is 2. Then plus 2 to the power of 4 and plus 0, that's 16. Then times 2 times 2 times 1, then times e to the power of negative 0, that is 4. And the last term, since we have the z, so it's 0, then times 2 squared times sine of 0, that is also 0. So the partial derivative of u with respect to s evaluated at 2, 1, and 0 equals to 192. And that is the end of the lecture. In the next lecture, we are going to use the chain rule to derive an equation for the implicit differentiation for multivariable functions.